Section 8.1, we're talking about something that you guys have all done before because you do this in Algebra 2. And then we did it again. No, you did it in Algebra 2. And then you did it again in Advanced Math for those of you who took that class. So you have definitely seen this before. And in Algebra 2, we hit it first semester. So it was before COVID for those of you who were in Algebra 2 during the COVID year. Systems of linear equations. Systems just means multiple equations put together that have the same variables, so they have the same solutions. So we're talking about, in this case, linear systems, and that is two lines, two equations that are both linear. So if you graph them, you get lines. So what we want to do first of all is talk about, for a system of linear equations with two variables, exactly one of the following things could happen. Now, before we go on, let me explain. When you graph an equation, you make a t-chart, right? Or you can make a t-chart. And you choose x values, and based on those x values, you get y values, right? Yeah. So every x and y coordinate that you have on the line makes that original equation true. Does that make sense? Because that's how you got it. You picked an x value and you figured out what y value makes the equation true. And so every point on that line makes the original equation true. When we are solving a system, our goal is to find a point that makes both equations true. So if you think about what we're doing, we're trying to find the intersection of the two lines. Does that make sense? Yeah. Okay. So we have three possible things that could happen. The first thing that could happen is you might have two lines that intersect. And if they intersect at one point. So you might have one solution. And if the system has exactly one solution, it is called an independent solution. That means the two lines intersect, and they intersect at one point. Another thing that can happen with two lines when you graph them is the two lines might be parallel. And if the two lines are parallel, how many solutions do you think they're going to have? None, because they never cross. There's no point that makes them both true. That is called an inconsistent system. The third thing that can happen when you're talking about equations is you might have two separate equations, and when you graph them, they're actually the same line. And so in that case, we have infinitely many solutions. And if there's infinitely many solutions, we say that that system is a dependent system. That means that both equations are actually equations of the same line. So they all have the same solutions. Okay, those are our three options. Two ways to solve them, and we've done these in the past. First way is the substitution method. You isolate or you solve for one of the variables. Then you substitute. Then you substitute. After you get that variable by itself, you substitute into the other equation. And after you've done that substitution, now you have a new equation that only has one variable. And once it has one variable, you just solve for that variable. After you solve for that variable, then you can substitute back and figure out what the second variable is. So in the first step, you'll substitute, and you might figure out what the x value is. Let's say it's a 10. And once you have that x value and you know it's a 10, then you plug it back in to figure out what the y value is. Okay? Is there somebody out there?
Oh, is it for your book?
Oh my God.
Oh, for your book.
Who do you need?
Anna.
Okay, go for it.
Don't smile.
The second method we have is the elimination method. And in the elimination method, first of all, we have to adjust the coefficients so that they match up to be exact opposites. So either you want the x's to be exact opposites, or you want the y's to be exact opposites. It doesn't matter which one. Just get one of them to be exact opposites. Pick the easiest one. And once we have that, we're going to add the equations together so that those variables cancel out. And once again, once they cancel out, you will have only one variable, and you'll be able to solve for that one variable. Once you solve for that one variable, you plug it back in and find the value of the other variable. So either way, you've got to solve for one of them first, and then you plug it back in to solve for the other one. Okay? You remember seeing this before and doing this before? All right, well, let's get to some examples. First example, if I'm looking at this one, and I don't particularly care for substitution, so I usually go with elimination, but this is one that substitution wouldn't be too bad, because it's pretty easy to get this top y by itself, right? We could do that by just adding y to both sides. And then we would have the equation y equals 3x. Okay? once we know what y equals, we do our substitution. So we go to the other equation, 5x plus 2 times y equals 22. We make our substitution and we replace the y with 3x because they are equal to each other. And in math, to make that substitution, they have to be equal. It's like if you go to a change machine and you put in your dollar and it gives you 4 quarters. That's okay because that's equal. They're equal values. Once we have this, then it's just solve for x. 5x plus this becomes 6x equals 22. 11x equals 22. We divide by 11 and x equals 2. After we know that x equals 2, we plug it back in. Usually that's the easiest spot to plug it back in, the one that you had already isolated. And we know that y will equal 3 times the x value, which we just figured out was a 2, and that is 6. When we write our answers, we want to write it as 2, 6 because we are emphasizing that this is a point on the graph where these two lines intersect. And they intersect at that one point, which means it's what type of a system? Independent. That is correct. So you'd be drawing two lines that intersect at one point, and that is an independent system. So far, so good? Great. Next one. In this one, I would definitely not choose to do elimination, or I mean substitution, because if you try to solve for any of these variables, you will get fractions, right? Even the simplest one here, trying to solve for the y, you'd end up dividing by 2. That would be okay. That would give you a fraction. I mean, or you can make it a decimal, so it might not be too bad. If you solve for the 3, that would be okay. That would be a fraction. So no matter what, when you are dividing those, you'd get fractions. So probably elimination would be the best option. Okay? So looking at this, we want to pick the one that seems the easiest. Now you chose y's to eliminate the y's. Why did you choose that?
Because they're smaller.
They're smaller, okay? So you can make both of the y's into what? 6's. And notice they already have different signs, which is what we want. We want them to be opposites. So what would I have to multiply the top equation by to make this into a 6? A negative 6. So we'd multiply by 3. What do we multiply the bottom one by? 2. Now we have to multiply everything by 3 and everything by 2. So we're going to get, or everything in each equation. So we're going to get 24x, and then multiplying by 3, we'll get negative 6y. And then multiplying by 3, we'll get 15. This one right here is the one that usually people forget about. They forget to multiply that one on the other side. So make sure that you don't make that error. For this one, we multiply by 2, we get negative 24x. We get positive 6y, and we get 14. So we're going to add these together. Now, we made it so that these y's cancel out. But what happens with the x's? They also cancel out. Now, what does that mean about the left-hand side of our equation? It is a 0.
What?
The left-hand side is a 0 because 24x minus 24x is 0. Negative 6y plus 6y is 0. So the left-hand side is 0. What about the right-hand side? No, you're adding. So 29.
Oh, so it is no solution.
So 0 equals 29.
False.
That is a false statement. Okay? So make sure we understand that this is a special case. When all the variables cancel out, that's one of our two other cases. It means there's either no solution or infinitely many solutions. Okay? Does that make sense?
Yeah.
Now in this case, is this true?
No.
No, 0 does not equal 29. There's no way 0 can equal 29 because there's no variables to adjust it. So this is not true. It's a no solution. Which is, it means that our system is inconsistent. That is correct. So if we were going to draw this, what do the lines look like? They're parallel lines. It doesn't say, but it is going to be on here when I pop up with the answer. So this is an inconsistent one. It has no solution. And again, the idea is those lines would be parallel. So that's why they don't ever intersect. Okay, does that make sense? Now, if this was a true statement, if you got like 10 equals 10, then that would mean infinitely many solutions. That means they're actually the same line. Okay, and we'll talk about that later. So which variables do you want to try to, and actually in this case you could use substitution, but like I said, I really don't like substitution unless it's practically already by itself or is already by itself. 3 and 4, what can we make both of those into? 12. So let's multiply by what on the top? Okay, so you're going to make that one negative and the bottom 3, so that one will stay a positive, and we need them to be opposites. So this is good that we have the top being a negative 12, the bottom being a positive 12. So we multiply, we get negative 12x, we get positive 24y, and we get negative 48. On the bottom, multiplying by 3, we get 12x, we get negative 24y, and we get 48. So here is when we're going to talk about this, because what happens on the left? 0, because everything cancels out. What happens on the right? 0. So this time, all the variables are gone, and we have a true statement. That means we have infinitely many solutions. Now, it's very important we understand. It doesn't mean that every ordered pair is a solution. It just means we have infinitely many of them. Because every point on the line, which goes on forever, is going to be a solution to both, because they're both the same line. This is a dependent system. Now, when we do this, and I know we haven't done this necessarily in the past, but we're moving on, and we need to describe the solutions. So here's how we describe the solutions. We just take one of our equations, and it doesn't matter which one. Let's pick the top one because it's smaller numbers. And we change it so that it's written in slope-intercept form. So can you guys do that for me? What do we need to do? Subtract 3x. So negative 6y equals negative 3x plus 12. And then what? Divide everything by negative 6. So y equals 1/2 x minus 2. So everybody's okay changing something into slope-intercept form, right? Yes. We've done that for several years. So then the way we describe our solutions is this. We can choose any value for x. So we just put in some variable. I usually use a's. The answers, they use t's. It doesn't matter. But just like in a t-chart, when we got to choose x values, what did we do with those x values once we chose them? We plugged them in. So what we do is we plug that in. We'd have 1/2 a minus 2. And so our solution set is anything that has this form. Once you choose an x value, if you plug it in and it equals that, that's the y value. So anything that has that form, we can generate an infinite number of possible solutions. Okay? Because you could put in an infinite number of different values for x. We don't like to use x's because, and I don't know exactly why, but I think it's to get away from the original equation and to get to the fact that you can use any number for x. I can't tell you exactly why, but they typically use something other than just an x. I think it's because we've got our x, y coordinates and they don't want to, I don't know, they don't want to get that messed up or something. Okay, so dependent, parallel line, or the same line, and that's our.
So if it's dependent, that's what we do?
Yep.
We have to
just put in slope-intercept form. Yep, and then put an a in for the x or whatever letter you want to use, and then write the other equation. Example 4 here, we've got a system of equations. It is still linear, but we've got fractions. And we learned earlier in the year, because typically we don't like fractions, we learned how to get rid of the fractions, right? So what can we do, and we do each one separately, but what can we do maybe to eliminate the fractions in the top equation here? What could we multiply by? Not the reciprocal, because if you multiply by the reciprocal of one of them, it'll turn the other ones into fractions. You just multiply by what number you need to multiply by to make sure those denominators cancel. So if I need to cancel a 3 and a 5, we would multiply by, in this case, 15. Does that make sense? So we're going to multiply everything up here by 15. And if you want to use a calculator for this part, that's fine. But 15 times 2/3 gives us 10x. And then minus 15 times 1/5 is 3y. And then 15 times 3 is 45. So that's the top equation. Looks much nicer now. We go to the bottom equation. What could we multiply by this time?
8.
You could use 8. Is there anything smaller? 4 will actually work, right? Does that make sense?
Oh, never mind.
You could use 8 and it would work, but you don't have to use
No.
something that large. Okay, but yes, I mean, if you use the denominators and just multiply by both of them, that will always take care of the problem. Or the fractions. Not the fractions are a problem, but. So this gives us 2x and 3y, how convenient, and 4. So does it make sense we're actually ready to eliminate right now? The 3's will cancel. So we're going to get 12x. The 3's will cancel, the 3y's will cancel, and we get 49. What's our next step? Divide by 12. I guess it shouldn't be too terribly surprising that if we had fractions in the beginning, one of our answers might be a fraction. But x equals 49 over 12. Once we have that, we want to go back and we want to solve for y. Which of the two equations do you think would be the second one? Smaller numbers probably. So it goes better with 12. Okay, so 2 times 49 over 12 plus 3y. Oh, you were going to use the fraction one? Yeah, I would just use the non-fraction one is better, I think, but it would have worked either way. When we multiply the 2 times 49 over 12, we get 49 over 6. And what do we have to do to continue solving for y? Yeah, subtract 49 over 6. Now, in order to subtract those, you can use a calculator, but I don't have one here. So I'm just going to get a common denominator. And 4 is 24 over 6. So that's gone. So 24 over 6 and a negative 49 over 6, we combine those, we get, let me move this up here. 3y equals negative 25 over 6.
Divide by 3.
Okay, so this is 4 over 1, right? So to get a common denominator, we need a denominator of 6. We multiply by 6. We have to multiply top and bottom by 6.
You multiply by a third.
Okay, you can just use a calculator too if you want.
Yeah.
Yeah.
Can I go get my car ready for my senior picture?
What?
That picture. She got best car. And she doesn't have her car.
Oh, so you have to go get a picture taken with your car?
Yeah, it just moves it over to the circle drive.
Okay. Yes, go ahead. And then, because we have fractions, you're right, several of you have said this, instead of dividing by 3, which you could do with a calculator just fine, but by hand, it's easier to do what?
Multiply by a third.
Multiply by 1/3, because it is the reciprocal of 3, and it will cancel, and this will give us y equals negative 25 over 18. So that means our solution is that x equals 49 over 12, y equals negative 25 over 18. And how many of you are nervous about an answer like that?
Me.
Yeah.
I was. So what can you do to figure out if it's the right answer?
Sub it back in.
Yeah, plug it back in and make sure that it gives you a true statement. So 2/3 times 49 over 12 minus 1/5 times negative 25 over 18. And I happened to do this in the first class. It does equal 3. And the same thing with the bottom, and it does equal 1. So you can always check your answer when you're dealing with systems. You can check your answer to see if you have the right answer or not. And usually it's just a matter of typing it into your calculator. So what type of system is this one? Independent. We got one solution, correct? So independent system, it's 2 intersecting lines. And 49 over 12 and negative 25 over 18. Okay. That was terrible? You love fractions that much, huh? Are you glad that we didn't just stick with the fractions the whole time? Okay, what about this one?
No, actually, wait.
What can we do here to get rid of the fractions? Multiply by 6. Good choice. So that's going to give us 2x minus, that's not right, 3x minus 2y equals negative 6. Now down here we have to be careful because notice the order is not what we normally have. So the negative 3x matches up with that one, and the plus 2y is going to be lined up with that one, and then we have a 6. So what happens again? Chop, chop. We get 0 and 0. So what does that tell us? Infinitely many solutions.
Oh, that's right, 'cause I forgot to do that.
And again, when we have infinitely many solutions, we want to describe what those solutions look like. So we want to take one of these equations and rewrite it into slope-intercept form. So let's probably just go with this one. What would we have to do? Add 3x. 2y equals 3x plus 6. And then what? Divide everything by 2. So y equals 3 halves x plus 3. And once we have that figured out, we know that our solutions will look like this. X can be any number we choose. And once we have chosen it, what will the y value be?
3/2a plus
3 halves times the x value we chose, which is a, and then plus 3. Okay. We're ready for Drew's favorite. Any questions on example 5? Okay. So guidelines for modeling with systems. And yes, we are talking about word problems here. So first thing, identify the variables. Usually you can figure this out pretty easily by looking at the question that you're being asked. And there's usually one or two things you're being asked, and there's usually two things we have to work with because we're dealing with systems. You have two equations, two variables, and yeah. So if you look at what the question is asking, usually that's kind of a giveaway to what you should choose for your variables. Then we express any unknown quantities in terms of those variables. So we want to write down what is each of our variables going to mean. Then we set up our system of equations. And finally, we're going to solve the system and interpret the results, which means we want to make sure we answer the question. We don't just say x equals 5 and y equals 2. We want to answer the word problem, the question that they're asking in the word problem. Does that make sense? All right. So let's get to the first one here. It says, a local buffet charges $7.50 per person for the basic buffet and $9.25 for the deluxe buffet. If 27 diners went out to eat and the total bill was $227 before taxes, how many chose the basic buffet and how many chose the deluxe buffet? All right. So what are we going to want to represent with our variables? Yeah, and it's not just the basic buffet. It's the number of people who chose the basic buffet, right? And the number of people who chose the deluxe buffet. So knowing that, we know this is the number of basic buffets, this, and let's just call that B. And then this one will be the number of deluxe buffets, and let's call that D. We're going to be very creative here. Use capital letters then. All right. So when we deal with systems, we need to come up with two equations, and they're usually dealing with two different aspects of the problem. Okay. Now notice here, we talked about two different things. We talked about how many people went out to eat, and we talked about how much it costs them to go out to eat. Does that make sense? Mm-hmm. So one of our equations typically will deal with the number of people, and the second one with the amount of money. So can anybody come up with an equation for us? We're going to need two. Or in this case, B plus D equals 27. You can use whatever variables you want. Just make sure they're labeled so you know what they are. Does that make sense? Yeah. The number of people who chose the basic and the number of people who chose the deluxe added together are 27 because it said 27 people went.
So then you can do 750B plus 925B.
Okay. Okay, so let's start with this. Can you explain to me why you did 7.5 times B?
Because that's how many per B person.
Yeah, the price times how many were purchased, right? Yeah. That gives you the total amount of money brought in by the basic buffets. Mm-hmm. Plus, and you guys already told me, 925 times D. And that's the same idea, the price for each deluxe buffet times how many people purchased that. And then the total is $227 because that was the total amount for that they spent.
And then the easiest one is going to be substitution.
Yeah, in this case, probably the easiest would be substitution. So what variable, and I'm going to go with the top equation. What variable would be the easiest one to get by itself? Yeah, they're the same. So get the B by itself, subtract D. So B equals 27 minus D. So now we are going to go over here and we're going to replace the B with what we just found out, 27 minus D. Plus 9.25 D equals 227.
You're not good enough for this.
Write smaller.
I am writing small. You write smaller.
Okay, but then you won't be able to see it.
And then we'll be mad at you. Full circle.
Write as small as you can.
How does that work then?
It doesn't.
You just told me to write smaller. If I do, you'll be mad at me. Okay, that makes sense. All right, so what do we need to do next?
Combine.
We want to distribute first, and then we can combine our like terms. So 7.5 times 27. Anybody got that? My calculator seems to have disappeared again.
Is it in your bag with the test?
No, it was here earlier today. I think somebody must have, oh yeah, I gave it to somebody to use during the test, and it's right here. 202.5? 202.5 minus 7.5D plus 9.25D equals 227. Then we can combine like terms. So 202.5 plus, I think, was that 1.75?
Yeah.
D equals 227. And then we need to subtract. So 1.75D, and we're subtracting this. And it looks like that should be 24.5. And then our final step, and hopefully that comes out evenly. And what is it? You like to say that over and over again. 14. So D is 14. Remember what D stands for? Number of people who ordered the deluxe buffet. And we can just subtract, and probably in our heads, 27 minus 14 from this right here, and we get 13. So what does that mean? 14 deluxe buffets and 13 basic buffets. And that is our answer to the question. How many people chose the basic? 13. How many chose the deluxe? 14.
Which would you choose?
I don't know what they have to eat, so who knows?
What kind of buffet?
Are we talking Chinese?
No idea. Pizza buffet, Chinese, Golden Corral, you know.
They do take it like that. They used to finally go.
That's why there's
They're gonna do like this.
Any questions?
I said sorry.
That thing that we have to do tomorrow, is that difficult? Am I going to struggle if I'm not in class?
No, I don't think so.
What time do you leave tomorrow?
I actually haven't seen your side of it, so I don't know for sure, but it shouldn't be hard.
You sent out an email. We have to.
The class survey?
Yeah, the evaluation. I don't think it should be very hard. It's just like answer different questions on whatever. Like I say, I don't think it's like that. I think it's more like, I don't know. Like I say, I've never seen your side of it.
I know what it is. It's like
How did you find this class? Well, I looked at my schedule, I found the classroom, and I went into it, and that's how I found the class.
His name's on the, I found his name on the wall.
His name is on the wall. Okay, example 7. A 10% salt solution is to be mixed with pure water to produce 75 gallons of a 3% salt solution. How much of each are needed? So once again, they're kind of giving us a hint. What do we want to use for our variables? What are we going to figure out? How much salt and how much water, right? So this is going to be, one of them is going to stand for the salt solution, and one is going to stand for the pure water. All right, what variables would we like to use? Of course you would choose S.
I don't want to. Let's go with W.
All right, S and W, Southwest. All right, now again, we have to have two equations. What are the two things, two pieces of information that they give us here?
10%.
So they're giving you percentage of salt, and then what's the other thing they talk about? 75 gallons, the amount, right?
Yeah.
So can we come up with a couple equations for this? Okay, the easy one is the amount of salt solution plus the number of water is supposed to equal 75 when we're done. Okay?
10.1 S
Okay.
plus 0.03 W equals.
Okay, wait, hang on. So 0.1 S, because the salt solution is 10% salt,
Oh wait,
plus
right?
how much salt is in the water?
None.
None. So 0 W
Plus
equals
3%.
0.03 times, because remember this is, yeah, 75, the total. But does it make sense? This is the number of gallons of salt solution, so 10% times the number of gallons of salt solution, 0% times the number of gallons of water, and then 3% times the 75 gallons total, because your end solution is supposed to be 3% salt. So I would use the bottom one first, because what happens to the W? It goes away. So let's just solve for S, and how do we do it? Well, let's do one step here first. What is 75 times 0.03? If I remember right, is 0.225, is that right? Okay, and then what do we have to do?
2.25.
So S is 22.5. Okay, once we have that, we can go back up and figure out what W is, because 22.5 plus W will equal 75, and we subtract, and what do we get for W? 52.5. Now, again, we want to make sure that we answer the question. So the question was asking how much of each?
I don't really understand the wording of this.
Well, we need 52 points.
What do you mean?
If I looked at this and you didn't explain it, I wouldn't have gotten it
I
because
don't know what it was meaning, what it's meaning, but.
Okay, let's draw a picture. So we've got this big container, and when we're done with the big container, we're going to have 75 gallons of stuff. They are telling us that that 75 gallons of stuff is going to be 3%.
75 gallons with 75 gallons of water, but it doesn't mean 75 gallons of all this stuff.
Right. So to produce 75 gallons of 3% salt solution,
What do you mean by of a 3% salt solution?
it means that 3% of that 75 gallons is salt. So you know how they mix?
so it's been diluted from the
It's, yeah, so the idea is you're pouring in water, and you're pouring in a salt solution that's 10% salt. So this is saltier than they need it to be. So they're going to mix it with water so that when they get done, they only have a more diluted salt solution. Okay, so does that make more sense? So that's, you're kind of dumping these things together, and you're going to use, some of it's going to be water, some of it's going to be that 10% salt solution. Okay, so again, to answer the question, how much salt solution were we using? Well, we're using 22.5 gallons of the 10% salt solution. And then we're using 52.5 gallons of pure water. And they have to put that pure water in there because then you know it's 0% salt, because
Yeah.
you know, even like normal water, if you soften it, it has salt in it, because that's how they soften it.
Oh, we're finished?
You know, have you ever seen a softener?
Yes.
You have to dump, believe me, you have to dump tons and tons of salt in it.
The only thing that registered was soft water, and I was just kind of trying to process that for a second. I know what it is. But like, that you don't have soft water. The only thing that registers is soft water.
Okay,
It exists.
so tomorrow, remember, we're going to be filling out that evaluation, so however long that takes. And then the rest of class time, it will be a work day for our 8 problems here that you've got to work on. Some of them are just straight systems, and then a few of them are going to be word problems.